Hello everyone. In this series again, I'm starting a new topic which is fault analysis in power systems. So, let's get started. So, what is a fault analysis? So, fault is nothing but failure of insulation. So, what is insulation? Insulation is nothing but if you have a so again I should explain what is insulation. So, if you have a high voltage component. So, for example, a transmission line or a transformer or whatever inside the conductor which is carrying the high voltage component, the high voltage has to be protected from getting accidentally connected to a low voltage part. So, uh, for example, this is a transmission tower. So, this is insulation is nothing but material between high voltage and low voltage parts to avoid unexpected flow. So in simple terms, insulation is nothing but you have this simple wire. So wire is this is a copper conductor. It is carrying the current. So this is actually a bare copper conductor. Now above that there will be some kind of a uh, covering, so this is like your protection, so that the current carrying conductor, if it is touching any, if you keep it on a iron table or if you keep it on a metallic, if you just touch it to metallic surface, there will be a high voltage wire connected to a metallic surface, there will be a shock. So to protect that, we have this kind of a covering on a wire, so that is called the insulation. And when the insulation fails, we say the fault has occurred. Unexpected flow of current is the fault occurring. So another example I can give is like, consider transmission tower. So the transmission tower will have some kind of structure like this. So at this point there will be something known as insulators. In fact, the name itself is insulator. So this is nothing but a, it's not a conducting material. It is a high resistance material. This is not a current carrying this one. So whereas the current carrying conductor is actually hanging below like this. So this is going to the next tower. So there you have again the similar conductor, and then again it is placed on a similar kind of a tower like this. So I'm not drawing the complete tower there. So this is the high voltage. And what is the voltage of the tower? It is 0 volts, because the tower is typically uh, solidly grounded to the earth. So it is maintaining at 0 voltage. This high voltage may be as high as like 132 kilovolts or even 200 kilovolts. So that much voltage is insulated here. Now, due to some reason, there is some breakage or some kind of a uh, problem with this insulator. If there is a short circuit, the current normally has to flow this direction to the next city or whatever. But suddenly the current will take diversion, and then through the tower, the current flows into the ground where it is a short circuit. So this is what we call it as a fault. So whenever a fault occurs, so this is failure of insulation causes fault. So what are the types of faults? So we had seen this types of faults. So broadly, you can classify faults into two types. So one is balanced, balanced faults, that is three-phase faults, and this is unbalanced faults. So balance means three-phase faults. That means you have three lines, line to line to line. So the insulation between line to the next line to the next line, all three lines is broken, and all three lines are getting short circuited. So that is called a three-phase fault. And under three-phase fault, why it is called balanced fault? The fault current will be balanced because the fault is same for all the three phases. You can also consider LLLG fault also. All three lines are connected to themselves, and that in turn is connected to the ground. So this is the LLLG fault. So these are the two types of faults here. So under the unbalanced faults, so I can talk about line to ground fault. This is most common, and then line to line fault, and then line to ground fault. So these are the three types of unbalanced faults. So you have three lines A, B, C, three phases. So one of the phase, so for example, phase B getting connected to the ground. So something like what he had seen before. So let's say this line is phase B, and this phase B is connected to the ground. So it's a line to ground fault. So like that. Similarly, line to line fault is, although ground is not involved, two lines connecting with each other, the line to line voltage will be again as high as 132 kV, and then it gets short circuited. It's a unbalanced, results in unbalanced currents. So this, the study of unbalanced faults is not the subject for this video. Maybe we'll take it up in future videos. But in this video, we would like to look at the balanced faults conditions. What do we mean by fault analysis? So let's say I want to do some fault study or fault analysis. What exactly do we mean by that? So fault analysis is nothing but we are asking the question, what are the bus voltages and currents and line currents under various fault conditions. So this is the question we are trying to answer. That means when the system is operating under normal condition, there is no fault, and there are some voltages and currents that we are not worried about. Then suddenly there is a fault, three line fault or LLG fault or whatever. Under that condition, or even unbalanced faults, now following the fault, after the fault, how the bus voltages and line currents will change is what is the question. So can you imagine what happens to bus voltages? So bus voltages will reduce because the high voltage part is directly getting short circuited with a low voltage part. And if it is a bolted fault, that means the impedance of the fault itself is very low, then the bus voltage will become zero. Otherwise, if there is some small impedance for the fault itself, so whatever is the agent causing the fault, some if there is some impedance to that, so then it will be, but still the voltages will fall, and of course the currents will rise. So this is fault analysis. So if I simply under fault conditions, if I remove this and then say under normal operation, then it's a load flow study. What are the voltages and line currents under normal operation? This is a load flow study which I have done. So basically, fault analysis is kind of an extension for your load flow studies. What is the purpose? Why we are doing this fault analysis? So why we are doing this fault analysis is that the first thing is we want to protect the system following the fault. So for protecting, see, I'll just draw a simple diagram here. There is a generator, and the generator is generating some power, and it is connected to a bus bar. So I'm just drawing a box like this. So this is a circuit breaker. So that means it can break the circuit, it can disconnect the generator. Then there is another circuit breaker, then there is a transformer, then there is another circuit breaker, and then there is a transmission line, and so on. So this is like a part of the system. This is also one bus, and this is another bus. So all of a sudden, if there is a fault at this point, that means the fault is there on this line. So there will be a huge amount of fault current flowing on this transmission line. So I want to detect the fault current as early as possible, probably within 1 or 2 cycles, that is within just 20 to 40 milliseconds. I want to detect very fast, I want to detect fault has occurred and then immediately send. So, who detects the fault occurrence? There is something called relays. So, to set relays. So relays are the devices which continuously monitor, millisecond to millisecond monitor, keep monitoring the currents, and the moment there is a fault, relay will pick up the fault. And for relay to know that fault has occurred, you have to give a reference value. The relay will measure the current and compare with the reference value, and then based on that takes a decision. Yes, fault has occurred. Then the relay will inform the circuit breaker. So let's say there is a relay here, and will inform the circuit breaker, and then the circuit breaker will open. So by the way, here let me show one more circuit breaker here, and then of course the relay also I'll show here. So relay and circuit breaker combination is here. Now there are 4 circuit breakers. If you see, if I number them 1, 2, 3, and 4. Now this relay has picked up the fault current. Of course, the same fault current also flow in this current. So the same fault current will also flow everywhere right from the generator itself. The fault current will go to the fault. So this is the faulted part. There's a relay here also. There's a relay here also. Everywhere there's a relay. So which circuit breaker? All the relays detect the fault, and all the relays will inform to the respective circuit breakers. But then which circuit breaker should operate? So for example, circuit breaker 3 operates and it disconnects this particular line. That is not most best way of doing it. The closest to the fault, where the fault has occurred, only at that point we need to open the circuit breaker. So it is like if you have an injury in the fault, injury in the finger, so the operation cannot be at the shoulder. So the operation should be at the finger itself. So the closest to the where there is a fault, the reaction should take place. So not only relays we have to set the proper values, we will also have to coordinate the relays. So for coordination of relays. So here what happens is sometimes there a fault, the fault current is picked up by this particular relay circuit breaker 2, but then it will wait for circuit breaker 1 to take off action, and only after circuit breaker 1 fails to operate, then circuit breaker will operate and it will open. So that way there is a concept of relay coordination. It's a different subject altogether. But fault analysis is useful for doing the relay coordination. Also, another thing is the ratings of circuit breakers. Now, what is a circuit breaker doing? The circuit breaker actually has, it's like an enclosed thing. So it's enclosed with some kind of uh, either it's a SF6 gas or it's some kind of oil or whatever. So it's a completely enclosed chamber or something like that. In that there are 2 conductors. So let's say this is A and B. So there are 2 conductors attached like this, and the current is flowing through this. Now in the circuit breaker, what happens when there is a fault is detected? Then A will move backwards and B will move backwards, thereby creating a empty space in between, thereby opening the circuit. But whenever you open a circuit under high current conditions, huge amount of arc is created. So there will be a sparking, there will be an arc. So that arc has to be quenched. So that's why some oil or SF6 gas or whatever is there, that will quench the fault, the arc which comes out of the fault. Now the question is, what should be the thickness of this conductor A? What should be the thickness of conductor B? How much oil needs to be filled? What should be the dimensions of this chamber? So that I'm able to, so for example, if fault current is let's say 8000 amperes, and this particular circuit breaker is able to disconnect the circuit without any problem. But suddenly if the fault current comes 20,000 amperes, so the moment it tries to disconnect, the entire circuit breaker itself will blast, and it causes more fire, and that oil which is there, which spills the fire to the nearby equipment and keeps on spreading it that way. So we need to know how much is the fault current expected value in order to decide the circuit breaker rating. So if I did not choose the proper circuit breaker rating, then it may not operate under faulted conditions. So whenever you are designing rating of circuit, for all these things, the fault analysis studies are important. Okay, so this is very brief introduction to fault analysis. Yeah, let me also cover one more point in this before I go to example problems. So the point is, you study this generator. Okay, so the reactance of the generator varies during the fault. So what we have learned when we are studying the generator is it will have some reactance x equal to, let's say, j 0.1 per unit. So or 10%. So x equal to 10%. So like this we used to mention the reactance for the generator. But this reactance 10% is the reactance under steady state. So state and then the reactance and the symbol. So state is, let's say, steady state. So and also I'll also give the duration of the state. So under steady state, the reactance is nothing but the reactance of the this one. It is called synchronous reactance. Synchronous reactance of the machine. Symbol normally we use X or sometimes XS or X, whatever we are doing. And the duration is, suppose there is a fault occurred at time t equal to 0. So, and each cycle in a 50 hertz system, one cycle represents 20 milliseconds. So more than 10 cycles, we would see that it is considered as steady state. So even though there is a fault, the fault current has kind of settled to some value. So that is the steady state where the excess we are doing. Now, what are the other states? The first state is subtransient state, and the second state is transient state, and the third state is steady state. So under subtransient state, the reactance is called XD double dash. So reactance is, of course, is called subtransient reactance. So the symbol is XD double dash. And under transient, we say transient reactance, and the symbol is XD dash. So I'm not writing here just to save some time. So this subtransient state comes for 0 to 2 or 3 cycles, or sometimes 4 cycles, and then maybe 4 to 10 cycles is the transient state. And finally, when the DC component in the fault current has settled down, and the fault current only has the AC component, then we are saying we are in the steady state. So far, whatever load flow analysis earlier we had done, we looked at only the excess of the generator. So XD double dash is typically less than XD dash, which is in turn less than XS. So if the reactance is less, the current you can expect it will be more during this time. Now, why this difference is there? What is the why the generator varies and all? For that, you need to go into stability analysis and modeling of generator and all, which is kind of a different course and different study. So right now, for our purpose, we are doing this. And since we are talking about fault analysis, I'm interested in the immediate 0 to 4 cycles time period, that is less than 80 milliseconds of time period following the fault. So therefore I will be using the XD dash in my studies. So for calculating this fault current, don't use the regular reactance of the generator, use the XD double dash, the sub transient reactance of the generator for doing your calculations. So speaking of calculations, so with this brief introduction of what is a fault and all, we'll take up some problems, and then we'll try to find the fault current, etc. Okay, so let's begin by the most simplest kind of a question on fault analysis. So I have a simple generator whose subtransient reactance has been given as J 0.1 per unit with 50 MVA and 11 kVA as its ratings. Now, this particular generator is connected to a bus 1 and connected to a transmission line of J.15 per unit. And then there is a bus 2 here, and the fault occurs at the end of the bus 2. And couple of assumptions are given. System is on no load. That means before the occurrence of the fault, the system was completely unloaded, and therefore the before the fault, the current here is zero, and therefore because the current is zero, I can assume that there is no voltage drop here, and all the voltages are 1 per unit. So V1 is 1 angle 0 degrees and V2 is 1 angle 0. These are in per unit. So now the question is, if a three-phase fault occurs, find the fault current in the following. So Z fault equal to 0. So let's do two cases. Z fault, so it's a three-phase fault. So case A is Z fault equal to 0 and case B is Z fault equal to 0.05 per unit. So 0 per unit means, so you can also give J here, just reactance to the fault. So that means it's a bolted fault. It's also called bolted fault or solid fault. And whereas this one is a fault with an impedance. So how do we solve this problem? So it is quite easy, just because everything is given in per unit. So let's go ahead and draw the reactance diagram. So you can attempt, you can pause the video and try to solve this. So meanwhile, I'll try to solve this. So I'll take the first case where the fault impedance is 0. So there is a generator, and then I'm doing the reactance diagram. So I have two reactances, and then there is a fault. So this is J.1 and J.15. So here the voltage is 1, here the voltage is 1 angle 0. This is all before fault. And the moment fault occurs, what will be the fault current? So what we can do here is, if there is a fault occurring here, that means the whatever is the, like this voltage, whatever is there, it becomes 0 volts, and therefore I can just simply calculate what would be the current here. So what will be the current here? So in other way you can see is find the Thevenin's impedance looking into the system. So you short circuit this and the total impedance is J.25, and here the voltage is 1. So 1 by 0.25. So fault current will be 1 angle 0 divided by J 0.25. So this will be minus J4 per unit. So this is the fault current in the per unit flowing here. So this is a line to line to line to ground fault. So that much current is flowing here. Now, but if you want to know what is actual fault current, so because we have S base, so I base is what? So I base is 50 MVA divided by root 3 into 11 kV. So if I do this S base by V base, so V gets cancelled, K and mega I'll get in kilo amperes, 50 by root 3 into 11. So let me go to the calculator. So 50 divided by square root of 3, so again is again divided by 11. So 2.624 kilo amperes, 2.624 kilo amperes. So therefore the actual current, so actual fault current will be equal to minus J4 into 2.624 kilo amperes. So that will be equal to answer into 4. So 10.497. So let's call it 10.5 minus J into 10.5 kilo amperes, or if I want to write it as a huge current, 10,500 amperes of current is flowing. So this is huge current. Now, what if there is a fault impedance? So if there is a fault impedance, then that fault impedance will add here. So again, 1 divided by that. So you'll get I fault equal to, so this is A, and in B, fault impedance is J 0.05. So in that case, so I get 10 degrees divided by J 0.25 into J 0.05. So here I get 1 divided by J 0.3. So that will be minus J 3.333 per unit. So this is the fault current. And similarly, I fault actual. Actual fault current will be, so minus J 3.333 into 2.624 amperes, kiloamperes, so which is equal to 2.624 into 3.333, 8.7458. So 8.7458 kiloamperes, or I could write 8,746 46 amperes. So this is the fault current under the second condition. So this is how you calculate the fault. Now there is only one source of fault current, so therefore I'm having like this. If there is another source of fault current, then you can also find the from the other side also. So we'll also look at some kind of problems like that. So let's continue, and let's uh, look at one more thing. Here the assumption is that there is no load and all bus voltages are 1 per unit. So I'll prepare the second question such that that assumption is not valid anymore. So let me just prepare the question. Okay, so here is the problem. So what I have done is more or less maintained a similar structure, but then I have added the load at the bus B or bus 2. Now determine the fault current if three-phase voltage fault occurs at bus B or at bus A. So first case is what happens if there is a fault here, what is the fault current? Now before the fault, imagine that there will be a current flowing in this line. So there will be some current flowing in this line and then some current flowing into the load, and this is going on under normal operation. And voltage V2 has already been given and V1 delta 1 is not given. So remember, if you go back to our earlier discussion in this course, this is the easy problem. It is very easy to find V1 delta 1. Just simply find the current here and then find the voltage drop and add it. You can get V1 delta 1 easily. Imagine that V1 delta 1 is given and V2 is not given. Then even before you start fault current analysis, whatever, you will have to solve the load flow problem first using Gauss-Seidel method or Newton-Raphson method. Whatever you solve the load flow, find out what is V2, and after that you will start doing the fault analysis. But anyway, our life is made easy because V2 value is already given here, and it is relatively easier to find V1 value. Let's begin by actually doing that. So of course I'm beginning my solution now, but you may pause the video and you may find you may you may try it yourself. I think I am just end of this page, so let me just take this question to the next page. So all right, so let me begin my answer for this. So what we'll do is we begin by finding out what is V1. So for that, uh, pre-fault load current. So what is the load? 12 megawatt at 0.5 power factor leading. So because this is given, so and the machine rating is given 20 MVA and 11 kV, and XD double dash is also given. So I will assume 20 MVA as the system base, 11 kV as the entire. So there are no transformers in this again, so it is easy. So the base is 20 MVA and 11 kV. So therefore, what is the per unit value of this S? So so 12 megawatt divided by 20 MVA, that is S base. So that is 0.6 per unit, I believe. Yeah. So 0.6 per unit, and at zero point 0.5 power factor lagging. Sorry, power factor leading is given. So zero point 0.5 power factor leading. So if that is the case, then what will be the actual? So P by S is zero point 0.5. So because the power factor is the nothing but ratio between the active power and the total complex power. So therefore, how do I get P? So P is zero point 0.5 into S. So that is zero point 0.5 into 0.6. That is zero point 0.3 per unit. And how do I get the Q? Q is nothing but S square minus P square. So because P, Q, and S are in the right angle triangle, so S square minus P square will be Q, reactive power. So that will be square root of zero point 0.6 square minus 0.3 square. So how much that will be? So square root of 0.6 to the power of 2 minus 0.3 to the power of 2. So I'm getting 0.51 or 0.52. So 0.52. So let me just verify. 0.52 square plus 0.3 square. Okay. SQRT. Alright. So this seems to be correct. So per unit. Now what is the sign? So because it's a load, if the value is positive, that means it is a load. And therefore, but then because it is leading power factor, I should give the minus. So it will be minus because it is leading. So therefore, my final S is nothing but 0.3 minus J 0.52 per unit. So this is the load on the loaded bus 2. So and what is the voltage? Voltage is nothing but 1 angle 0 degrees. So therefore, the current is nothing but S conjugate divided by V conjugate. So that is nothing but zero point 0.3 minus J 0.52. So here I'll make it plus because of the conjugate. And then V conjugate is nothing but 1 minus 0 degrees. So it is just nothing but same. So therefore, the current is zero point 0.3 plus J 0.52 per unit. And once I know the current voltage drop will be I into X of the line. So J 0.15. So I guess that is J 0.15 and multiplied by the current I. So let me open a new program and then I'll solve here. So S equal to 0.3 plus, minus 0.52 I and V equal to 1. So this is V2. V2 equal to 1. So therefore I equal to conjugate of S divided by conjugate of V2. So let me run this. So 0.3 plus 0.52, that is correct. Then drop, voltage drop is nothing but I into 0.15 I. So I'm getting the voltage drop here, and then finally I'll find out the V1. V1 equal to drop plus V2. So finally I'm getting V1 like this, and let me also get the absolute value of V1, printf, or I'll just simply absolute value of V1 and then angle of V1 into 180 divided by pi. So 0.923 angle is 2.79 degrees. So you notice that 0.923 angle is 2.79 degrees. You notice that the angle is positive compared to this one. So angle is greater. So the active power P will flow in this direction. Whereas you see magnitude of voltage 0.923 and the magnitude of voltage is 1. So reactive power flow will be in the opposite direction in the same line at the same time. So this also we had seen before. It can happen in the power system that if there is a transmission line in that same line at the same time, active power can flow from left to right, whereas reactive power can flow from right to left. That can happen depending on the power factor of the load. So anyway, so let's come back to our problem. Now we have the pre-fault voltages. So now what happens if there is a fault at bus B? So when there is a fault at bus B, so right now we can just simply ignore the load. So because this load will carry 12 megawatt and all, provided the voltage is being supplied. But now I am having a bolted fault here, so completely this voltage will become zero. So this part we can simply ignore it. There won't be any current coming from this part. I will get current from only the other part. So here I am ignoring the load during this faulted period. If there is a machine here like a synchronous motor or synchronous generator and all, it will have an internal voltage. That internal voltage can feed a reverse current into the fault, but in this example that is not the case, so therefore we are not calculating that fault current here. This is assumed to be some kind of a voltage dependent kind of a load with a fixed impedance value. So when this fault goes zero, this current will not be considered. So let's look at this now. So what will be the fault current here? So again, I look at the Thevenin's equivalent. So there is a 10 here and there is a 15 here. So I'll get a Thevenin's equivalent something like this. This is J 0.1% and then, sorry, 0.1 per unit and J 0.15. And then here the pre-fault voltage is 1 and then there is a fault here. So, so again, exactly the same uh, calculation goes, that is okay, I think this is the time to explain the logic of Thevenin's uh, equivalent. So what we do is, I'll take two circuits. So one circuit is like this. This is pre-fault circuit and other is post-fault circuit. So pre-fault circuit is like this. We have this. This is our B point, this is our A point, and J 0.15, and this is J 0.1. This is the pre-fault. Now I know how much current is going here, I pre-fault. So let's call it I naught. So I naught we have just calculated, that is here. This current we know. Now under post-fault, what happens? So under post-fault, what Thevenin's theorem is stating is that I can put, see, I can just simply short circuit this. So if I short circuit this, what will be the voltage here? This voltage will become 0. So the same effect of getting voltage 0, I can also get something like 0 equal to 1 minus 1. So plus 1 minus 1 is also 0. So what I will do is I make two gaps here and then introduce two voltages like this. But here the sign is plus minus and minus plus. So the plus is here downwards. Now the voltage whatever it used to be here, that is V2, the same V2 I'll apply for both of this. So now this is post fault, this is coming correctly. So now what I want to do is, if I want to know what is the current, so under this condition, so there are three voltage sources. So this is the original voltage source. Let's say this is G generator, and then another voltage source here and another voltage. There are three voltage sources. So what I'll do is I'll calculate only, it's like a superposition theorem. First I'll consider this new voltage source, other two voltage sources at short circuit, and find out what is the current. So what is the current? So the current will be like this one. I'll just consider only, let's say this is V2, let's call this AV2 and BV2, or XV2 and YV2, something like that. Consider only YV2. So I'm doing superposition. So superposition theorem, one voltage source at a time you will consider. So I'm only considering this. So this is short circuited. Then I get something like this, J0.1, J0.15, and then this is short circuited, and then below is the plus, above is the minus, and then I am having like this. Now this side anyway is, this is there, load is there. So here the voltage is V2. So V2 I already know, V2 voltage is 1 angle 0 degrees. Now what will be the current? So this current, considering only this voltage source, I can calculate like this. So of course some other current, the current will also flow like this. Now this current which is flowing in this part of the load will be exactly equal to the, equal and opposite to the original current. Therefore these two will cancel out each other and there won't be any current here. We don't worry about that now. So let's worry about this one. So let's call this as IF current. So what is IF here? So it will be again 10 degrees divided by 0.1, 0.25. That will be 10 by, sorry, this is 15. So total will become 0.25. It will become minus J4 per unit. But the direction of this current will be like this. Now, because the minus is there, plus is there, it will be like this. Now, I go back to this, and here V2 is 1.0 per unit. Now, this voltage source I will consider here, plus minus. Now, V2 equal to 1 per unit. What will be the current in this voltage source? The current in this voltage source will be actually 0, because already this point is maintaining the same voltage. So if, even though it is just maintaining same voltage, if I just consider this, it will not, there is no potential difference here, so no current will flow in this branch. So it is like in a network, already the voltage at this point is 7 volts. So then if I connect a 7-volt battery, it will not cause any additional current to flow to that, because already this is plus 7, this is plus 7, so no current will flow. It is something like that. But now what you see, the current we calculated earlier, I naught, already considered these two sources. So two sources already considered. Third source just now I have considered. Therefore, the net superposition current that will flow will be, so net current will be nothing but I naught plus IF. So in fact, I would call this delta IF, delta IF, delta IF. So what is my I naught? So I naught was 0.3 plus J 0.52. So 0.3 plus J 0.52. To this, I will add this one plus minus J4. So this is the way to, so this is the pre-fault current and this is the post-fault current, and this is how you consider systems where there is a load. So let me calculate the I fault here. So 0.3 plus 0.52 I minus 4I. So 0.3 plus 3.48 J. So this is the final net fault current. Now who is supplying this current? This net fault current is being supplied by the generator G1. So this generator itself is supplying that entire fault current. Now whole of this story is or this case is when the fault is occurring at when the fault is occurring at bus B. Now consider the case fault at bus A. So let me redraw the power system. So we have a generator. It has its own subtransient reactance, that is xd double dash equal to 0.1, and this is your point A, and then there is J 0.15, and then there is a point B, and then there is a load here, and then finally now the fault has occurred at this point. So when the fault has occurred at this point, what you will consider? You will be considering a voltage here, another voltage here, and this will have plus minus, minus plus, and then you short circuit these two, and then simply find the fault from here. So now on the right side, this path you will neglect. So from left side, how much current is coming from the generator? That's what you're going to see. And what is the value here? So this value is we calculated already. That's why we calculated this thing. So this one, 0.923, 2.79 degrees. 0.923, 2.79 degrees, and this is also 0.923, 2.79 degrees. So now what will be the fault current here? So this is delta IF. Considering now I short circuit these two, and then just calculate the fault current in this branch. So delta IF will be equal to 0.923 angle 2.79 degrees. So notice that this is plus direction, so therefore the current direction is also like this. So the impedance is only J 0.21. So therefore the current will be minus J 10.23 angle 2.79 per unit. This is a very high current is like this. Now whereas earlier the current was already I naught. So I'll add the net current. So it will add to I naught. So I naught plus delta IF. So 0.3 plus J 0.52 minus J 10.23. So 10.23. So it will be 9.7. So this is my new fault current considering the load. So I hope you're getting just some idea about how to solve systems with how to find the fault current when the system load is given enough. Okay, so we will do some more parts in this series, and we'll take up one more problem and we'll try to study it completely. Also, there is a role of bus impedance matrix that is also going to come in our next video.